and the kinds of things that you see. Okay, let's look at this laccolith here. Here's a laccolith at the surface. It's been exposed, it's been exhumed. This is how it was emplaced, as this big laccolith originally. Now all this cover rock is gone, and even the surface of the laccolith has been kind of eroded, and now it stands up on the surface. Is that huge mountain. It's the Henry Mountains out in Utah. That's how big a scale some of this stuff is. These aren't just little blips and things the size of rooms. These are huge when they get exposed. Another thing that happens that's kind of cool is the way these things literally cool off. They start to cool from the edge. And the last thing that cools is the center, because that's been surrounded by all this hot rock. And you have to cool that off first before you can cool off the center. So it doesn't cool evenly. And as it cools, it shrinks. So part of the body is shrinking, part of the body isn't shrinking. And that means there's a lot of stress imposed on the body. And the way that's going to get relieved is the rock is going to crack. It's the same thing you see when they pour cement and they have to cut joints in the cement to keep it from just cracking all over the place. Same kind of shrinkage problem. Well, the most efficient way for the rock to do that is to crack into these polygon shapes, because that provides the best distribution of surface for the rock to cool most evenly. So you see that polygon cracking happen all through the body. And here you can see this beautiful example here. This is Giant's Causeway National Park. It's over in Northern Ireland. And it looks like somebody actually went out there and just stacked these columns next to each other. I mean, it looks man-made, doesn't it? But it's not. It's nature. It's just the way the flow of magma cooled off very efficiently and formed this polygonal structure system to get rid of the heat as fast and as easily as it could. So this is what we call columnar jointing. And whenever we see columnar jointing like this, we know it's a cooling phenomena from one of these big massive flows. Okay, so we talked about Devil's Tower here in Wyoming as being a big volcanic neck. And we talked about it as something with columnar joining here. If you notice, see all these stripes? These are all columns. This whole thing, if you were to look down on the top of it, you'd see the columnar pattern, and this whole thing is just a series of these columnar joints all through it. And you can see this whole neck is beautifully jointed during the cooling process. Okay, so I'm going to give you 10 seconds. I just told you the answer. Devil's Tower, besides being known for columnar joining, is also known for being what? See, this is why you want to stay awake in lecture. Okay. What is it? Only one person missed it. Okay, good. Yeah, it's going to be a volcanic neck. It cooled off very quickly, and when it did that, formed all this columnar joining. Oh, it's still going.
There you go. Everybody got it right now.
Yeah. The one person that didn't have it right got it right now. I guess we'll have to eliminate this one. Oh, no, no. Batteries must be getting bad in my clicker here. It's acting very strange. Okay. Okay. So, you're still working on my place, aren't you? So let's kind of take a look at some of the rocks around my place. What would be some of the things that you look for your slides? And around my place, it's all Precambrian granite. And what's really cool, in this one picture, you can see a couple of things. If you notice here around the kayaks, all the granites are kind of pink. And some of it's iron stains, and you can kind of tell that a little bit when you get a fresh surface. But it's still pretty pink. And that's because the granite in those areas have a lot of K-spar in them, a lot of that plagic or that potassium feldspar. But look back here at the color of the granite. It's all really gray. And not much potassium feldspar back there. It's mostly sodium feldspar. So we see a couple of different kinds of granite, and the color is directly related to just the change of a couple of minerals, sodium versus potassium feldspars. But the whole area basically is this kind of granite. So we're looking at the granites, and if I just change out a little of this pinkish K-spar for a little more of this whitish sodium feldspar, that makes all the difference in the granite color that you see up there. So we're looking at coarse-grained rocks, granites, so they're felsic. We're down here at the soda-rich end of things, or the silica-rich end of things, and we're looking at coarse-grained rocks. This covers most of northern Canada. This is a big batholith. It's the core of the North American continent. So this is a huge batholith, and it's got to be an intrusive plutonic rock because it's coarse-grained, and that means that there has to be at least 7 kilometers worth of rock on top of it that's gone. So the question is, where did all that rock go to? And the answer is all that eroded rock is making up a lot of the United States as sedimentary rock that laps up onto this old granitic core. Okay, here's the island, and if we take a walk from the cottage and go down toward the dock here, right in here there's kind of an interesting little feature. What's this thing? What is that? Here I've got this pinkish, and even you can kind of see some grayish bands of granite here. And all of a sudden, I've got this big black blob sitting there. And if you look at it, isn't it kind of weird that it's just such a straight edge here? And look, I've got a little of this dark stuff kind of streaked into the granite. And look how I've got this piece of granite that's kind of hanging in the end of the black stuff. Well, what we're looking at is a xenolith. This was the host rock, and it's broken off and fallen into the intrusive granite when it was all melted. And here I've got a little chunk of the granite that's kind of gotten almost surrounded and eaten up with the melting of the xenolith. So kind of some neat stuff going on here. One of these little chunks like this is sitting right there in the country line. Okay, so those are the kind of things you might look for when you're doing my place and you want to look at the rocks where you are. Okay, Bryce Canyon National Park. This is one of the neatest places around. And you can see how the weathering and erosion is cut down through all the different sedimentary layers, the sandstones here, all flat-lying sandstones. And you can just see how they're just getting dissected by the erosion. You can walk down through these slot canyons, these little bottoms of these stream beds, and look up, and it's just gorgeous. Bryce Canyon is one of 3 places that you want to put on your bucket list. Because remember when we were talking about time, we said you could go to the Grand Canyon, you could go to Bryce Canyon, and you could go to Zion National Park. And those 3 places, besides being beautiful, you could see the entire geology of the world, of Earth, from the Precambrian all the way up to the present day. Those 3 places stack on top of each other, hook together. You can figure out where they hook, and you can see all of the geologic history of planet Earth in these 3 spots. Bryce is a pretty neat place to go visit. Well, we've been talking about igneous rocks, right? So what we're going to do is change gears now. And instead of looking at things made from a melt, we're going to switch and talk about sedimentary rocks. Things that are recycled, pieces that are broken up, that have been transported, that have been sorted out, the materials have been kind of rearranged, they've been reaccumulated, and now they're going to get smashed back together, cemented back together, and we're going to make them into rocks, these little bits and pieces of other rocks. Sedimentary rocks. But before we can look at sedimentary rocks, we need to look at sediments, all the little bits and pieces that are going to make up these rocks. So we want to talk about how do these previous rocks get broken up, how do they get transported, sorted out, and how do we make these new sedimentary rocks? So that's what we're going to look at today. We often use the terms weathering and erosion. And in general, you hear people kind of using them synonymously to mean the same thing. But they don't. Weathering is the process that we use to break the rocks apart. Whether it's a glacier running over a rock, or it's just a stream breaking it up, or it's frost heave making a pothole. Whatever the process, that's weathering. And that's the breakdown of the rock. We can do it 2 ways. We can do it mechanically, which is basically beat it up with a hammer and smash it into pieces one way or another. Or put something on it that's going to dissolve it, and we can chemically weather the rock. Erosion, on the other hand, is taking those busted up pieces and that dissolved material and transporting it away from where we made it, or created it, and putting it someplace else. So weathering is the breakdown component of the process, and erosion is the transportation, sorting part of the process. So 2 very distinctly different things. And oftentimes we see rivers and glaciers, winds and waves. Those are the processes. Those are the things that create these issues of weathering and erosion. If you think about it, the processes are always going to kind of stay the same. Now, the rate might change, the intensity might change. For instance, in spring, when the stream is full of water, it's ripping up the banks, it's carrying trees down the stream, it's chocolate brown, muddy water. In August, it's barely a trickle. Same thing, same process. It's a stream, water's running downhill. It hasn't changed the process, but it has changed the rate or the intensity of the process. So oftentimes we see that as part of this erosion weathering issue. Okay, weathering, like everything, has positives and negatives. If you think about it, one of the positives is it breaks rocks down to where it liberates the minerals that make up the rock. And now all of a sudden we have minerals that can be added into soils, can make soils. That means we can start growing things. We can do agriculture. And we now can have minerals that we can ingest that are necessary for our maintenance, our well-being. On the other hand, man-made structures get pretty well eaten up. Roads get potholes. Bridges have to be replaced about every 20 years out on the interstate. It costs money to combat these things when it's working on things that you don't want it to work on. Can I go back a slide? You're just not writing fast enough, huh? So basically, you know, it's like everything in geology. There are pluses and there are minuses. Just kind of depends what side you're on. Okay. So when we think in terms of weather, we think in terms of either mechanical weathering or we think in terms of chemical weathering. Mechanical weathering, look what's happened to this rock. You can see how it's been shattered. It draws heat. The cooling, contraction, the heating, expansion has broken this rock apart along its original bedding planes. Or here's a piece of calcite. I'll put a little drop of weak acid on it. You can just see how that base acid reaction is causing it to fizz and bubble, creating water and vapor. So I'm just breaking the material down. And now it's easy to wash that off of that mineral, and I've got a smaller piece of mineral, and I've weathered and eroded that piece. So the name of the game, whether it's mechanical or chemical, is surface area. The more surface area that I can expose, the more area then can be weathered and eroded. And this is not a linear process. It's exponential. If I just take a cube and I chop it into, littler cubes, divide each direction by half, I go from 6 square meters to 12 square meters. I do the same thing again to each cube, and I go to 60 square meters. So this is an exponential thing. That means the rates of erosion and the rates of weathering are going to increase as the stuff gets smaller. I'm going to very easily start to see some significant changes. One big rock is going to weather and erode a lot slower than a bunch of little rocks. So let's kind of start at the cliff. And here I've got this cliff area up here. I've got a few little fractures where mechanically it's broken apart a little bit. And when it's above freezing, these fractures fill with water. And now we start fall and this water starts to freeze at night. And when it freezes, that water expands a little bit. Not a lot, but a little bit. About 9%. So what's going to happen to that water? Well, have you ever looked at water in your ice cube tray? You know that water was flat when you put it in the tray. But when you take the ice cubes out the next day, don't they kind of have a dome shape on them? Well, that was the expansion of water going to ice. In this case, it was able to simply dome up on the surface because there was nothing there to keep it from doing that. And it'll do that a little bit here in this crack. It'll tend to dome a little bit. But notice how it's freezing? It's freezing from the top down. So once this top is frozen and the bottom part continues to freeze, doming is pretty much at an end. And now, as that water freezes, it's going to have to start to push that crack apart. So every night when that water freezes up, that crack gets pushed apart a little bit. The next day it thaws out during the day. A little more water trickles into the crack. That night it freezes again. And little by little by little, that rock is broken apart. And all of a sudden, a chunk of this rock now falls off the edge of the cliff. And it falls down, accumulating at the base of the cliff. Where maybe when it's smashed onto the other rocks,